The sine rule. Proof. Recall that in any triangle ABC, the angles are denoted by capital letters and the sides opposite these angles by corresponding small letters. So this is what it means. So in any triangle, for instance, in triangle ABC, the angles are denoted by capital letters, and then so angles are denoted by capital letters, and the sides opposite these angles by corresponding small letters. That is, the side opposite angle A is A. So this is the angle A. And the side opposite angle A is the side A. So this side A is opposite angle A. So you denote the side opposite angle A with corresponding small letter A. Also, the side opposite angle B is denoted by B, and the side opposite angle C is denoted by C. So that's what it means. So the proof: all angles are acute. So there are two ways we get the proof for the sine rule. The first one is all angles are acute. So given any triangle ABC with all angles acute, as shown in the diagram above, I mean this diagram here. So we're given this diagram ABC where all the angles are acute. Our intention is to prove that A over sine A is equal to B over sine B equal to C over sine C. I'm going to use this triangle that we have been given to show that this relation is true. Now, what do we need to do for us to be able to prove this relation? We need to do a little construction, and that construction is that we need to draw a perpendicular line from C to meet AB at D. So let's do that. We're going to draw a perpendicular line from C to meet AB at D. So, okay. So once we produce a perpendicular and it meets line AB at D, it means that this angle is this line is a right. I will make a right angle with line AB since it's perpendicular to line AD, and this will give us the height of the triangle. The height of the triangle. Okay. Now, proof: in triangle ACD. So let's see triangle ACD. That means this triangle ACD. In triangle ACD, angle ADC, which means the angle here is equal to 90 degrees. So let's CD be H. So CD is H, which is the height of the triangle. So let's start with our proof. So say using sine ratio, which is from our trigonometric ratio of a triangle, we know from SOHCAHTOA, you know that SO is a sine ratio, and S in SO means sine of the angle is equal to O, which is opposite, over hypotenuse, which is H. So that's a sine ratio. So using sine ratio in triangle ACD, so sine A, which is this angle, sine A is equal to opposite H over B, and H is equal to B sine A. So let's call this our equation 1. So in triangle BCD, so this first one was gotten from triangle ACD. So I'm going to use a triangle BCD. Using sine ratio, let me put it this way: in triangle ACD. So in triangle BCD, sine B. We are looking at this triangle now, BCD. So what we got was that when we drew a perpendicular from C to meet line AB at D, the perpendicular share this whole triangle into two triangles. So initially it was triangle ACD, but the moment we drew a perpendicular from C to D, we got two separate triangles, which were triangle ACD and triangle BCD. So now we first of all gotten the sine ratio for sine triangle from, we got the sine ratio which was sine A equals to H over B from triangle ACD, which is ACD. Now we are going to get the sine ratio from triangle BCD. So in triangle BCD, sine B is equals to the opposite H over hypotenuse, H over A, and that will give us H is equal to A sine B. So let's call this equation. So let's say from equation 1 and equation 2, we have from equation 1 we have, so since both of them are equal to H equal to sine B sine A and H equal to A sine B, both of them are equal to H, they are equal. We have here from 1 we have A sine B is equal to B sine A. Reason is that both of them are equal to H, which is the height. That's why they're equal. So from here we can simply divide. We can simply divide by, so this becomes cross multiply. So divide by sine A and so on by sine B. So give us A over sine A equal to B over sine B. And then when we multiply, we get this back. We cross multiply, this part multiplies this, and this part multiplies this, we get this relation back. So let's call this equation 2. Yes. Okay, so that's for this first part. Now what about this part? So for us to get this part, we can do something similarly. If we draw a perpendicular from B to meet line AC at, similarly draw a perpendicular from angle B to meet AC at E. So if we do that, we discover that it can also be proved that A over sine A is equal to C over sine C. This is equal to equation 4. So assuming we have this, let's say we have this triangle to this form, and this is, remember this is angle C, this is angle B, this is angle A, and okay, so this is side A, and then this is side B, and this is side C. So if you produce a perpendicular from D until it gets to a line AC at E, let me put this B here, side B. So this is line E. These are perpendicular, and then this becomes our height. This becomes the height of the triangle. So now initially it was just one triangle, but after we produce perpendicular from D to E, line AC at E, the perpendicular split the single triangle into two separate triangles with a single height. So from triangle ADE, we discover that if you use sine ratio, you get from triangle ADE sine A is equal to, sine A will be opposite H over C, which will give us C equals to, H will give us C sine A. So also from triangle BCD, CA, for triangle BCA, sine B, for triangle BCA, sine C will be equal to opposite, which is h over hypotenuse, h over a, and h which is h is equal to a sine c. Now, since both of them are equal, this will give us a sine c equal to next where h sine c is equal to c sine a, and that will give us, so when we go for that, this will give us a over sine a is equal to c over sine c. So it can also be proved that similarly, when we draw a perpendicular from B to meet AC at E, it can also be proved that A over sine A is equal to C over sine C. So when we combining equation 3 and 4, we're going to have A over sine A equal to B over sine B equal to C over sine C. So what does this give us? This becomes our equation 5, and this is exactly what we ought to get. We also this was what we're told to prove from the beginning, and that is it. So that's the sine rule. Alternatively, we can write this in this way. We can say sine A over the sine equal to sine B over the side equal to sine C over the side C. So either this or this, we can call this equation 6. So either this or this will give you the same answer. So that's the sine rule. That's the sine rule, the proof for the sine rule. The obtuse angle triangle. So we're going to carry out the proof for the sine rule on obtuse angled triangle. So given any triangle ABC with one angle obtuse, in this case B is obtuse as shown in the above diagram. So angle B is obtuse. So you need to know the difference between an acute angle and an obtuse angle. Acute angles are angles that are less than 90 degrees. Acute. Obtuse angles are angles that are within the range from 90 greater than, let's say theta 90 degrees. Theta is greater than 90 degrees, but less than greater than less than 180 degrees rather. So obtuse angles are in this range. They are greater than 90 degrees but less than 180 degrees. And then the other set is reflex. So reflex is within the range 180 degrees then 360 degrees. So reflex angles are greater than 180 degrees but less than 360 degrees. So for acute angles, you have, first of all, this is a perpendicular line. So when a vertical line meets an horizontal line such that the angle formed between them is 90 degrees, we call them a right angle. That's a right angle. That angle is a right angle. So if you make a triangle from this, we call it a right angle triangle. It's a right angle triangle. So this is a right angle. Now the next one is acute angles. Acute angles are usually below 90 degrees, so they are not exactly equal to 90 degrees. Any angle from this range from between, in this form, let's say theta, all this theta, all this alpha, call this beta. As long as they are not equal to 90 degrees, we call them acute angles. They are less than 90 degrees, which is this perpendicular, this angle formed, the angle formed between this vertical and horizontal. Then obtuse angles, as once the angle gets beyond this 90 degrees, this is 90 degrees exactly. So if we have 91, 98, the theta, and then it comes like this, let's say beta, then we have something like this, and let's say this is what gamma, whatever it is, as long as it's not it doesn't exceed angle at a point, it's on a straight line rather, which is equal to 180 degrees. As long as it doesn't get beyond this line, which makes angle on a straight line equal to 180 degrees, we call them obtuse angles. So obtuse angles are angles that are greater than 90 degrees but less than 180 degrees. On the other hand, once it gets beyond this point, when it's like this, any angle like this is called angles on a straight line. And angles on a straight line is equal to 180 degrees. So if the angle of rotation gets, let's say, just slightly get beyond this straight line and it comes like this, it's now more than 180 degrees. So this is a reflex angle. So this now reflex angle, and yes, it's another reflex angle. So all these angles, alpha, A1, A2, A2, they are all greater than 180 degrees, but they are less than 360 degrees. So by the time we bring the corresponding angle to this point, we have angle at the points. So that's the difference between acute angles and obtuse angles. So what we are given here is that one of the angles in this triangle is an obtuse angle, and this is it, angle B. So in any triangle ABC with one angle obtuse, in this case B is obtuse as shown in the above diagram. So what do we need to prove with what we have been given? To prove that A over sine A is equal to B over sine B equal to C over sine C. And what do we need to do in order to be able to prove this relation? Construction: draw a perpendicular from C to meet AB produced at D. So there's going to be an extension. We need to extend AB, which is this, to point D, and then we need to produce a perpendicular. So when we do that, we're going to have two separate triangles. So which is triangle A. First of all, we're going to have triangle ACB and triangle ACD together. So let's get into our proof. So in triangle BCD, here's our triangle BCD, using sine ratio. Now, if you're going to use sine ratio in triangle BCD, that means we are considering these angles BCD, and of course the angle we are going to look at is angle B. Now, if you look at this triangle, let me draw it clearly. This is angle B, the obtuse angle B, and this is what was produced. This is CB. We are considering triangle BCD, and you know, using sine ratio, sine is only sine of the angle B. So since you are considering triangle BCD, we don't have any. We are not going to use this angle, which is the obtuse. Rather, we need to know this angle. So how do we know this angle? So if here is theta, what would be this place? This place will now be 180 minus 180 degrees minus theta. Why? Because this is angles on a straight line. So if here is one at theta, this part will be 180 degrees minus theta. So that's what this will be. So in triangle BCD, using sine ratio, we're going to have sine. Here B, sine B is equal to sine 180 degrees minus B. This B is the obtuse angle B. So the acute angle B will now be 180 degrees minus B is equal to, so B opposite, which this is opposite because this is the angle. Any side that's facing the angle is the opposite, and this side is hypotenuse. So this will give us H over A, and then H is equal to A sine 180 degrees minus B. But sine 180 degrees minus B is equal to B. Why is it so? It's because sine 180 degrees minus B from our quadrant where we have A, C, T, S. From our quadrant, sine is positive in the second quadrant, and you know in the quadrant, this is 0 degrees, this is 90 degrees, and this is 180 degrees. So any angle from here to here, as long as it's within this range, is equal to 180 degrees. So, and here 180 degrees minus theta means that the angle is obtuse is greater than 90 degrees but less than 180 degrees. So the angles that fall within this range are positive, and sine in this quadrant is positive. So we can conveniently say that 180 degrees minus b is still the same thing as still the same thing as sine b, because sine is positive in the second quadrant. So we're going to say second quadrant. That's the reason. Sine is positive in the second quadrant. Okay. So altogether we're going to say therefore h is equal to a sine b. So this becomes our equation 1. In triangle ACD, using sine ratio. So next thing that we're going to consider is triangle ACD. That's this whole triangle ACD, not ABC. In triangle ACD, which is also an acute triangle, where two angles are acute. The three angles are acute rather. Okay, two angles are acute. So in triangle ACD, using sine ratio, so our opposite, now that we are going to focus on sine A. So sine A is equal to opposite, which is h over hypotenuse, h over b, and this will give us h is equal to b sine A, equation 2. So from 1 and 2, from equation 1 and equation 2, we have, since both of them are equal to h is equal to this, h is equal to this, that means both of them are equal, and that will give us a sine b is equal to a sine b sine a. So this will give us a over sine a is equal to b over sine b. So when you cross multiply them together, you get this back, and when you divide, you get this. So let's call this equation 3. So similarly, it can also be proved that a over sine a equals to c over sine c. So this becomes equation 4. So combining 3 and 4, we have a over sine a equal to b over sine b is equal to c over sine c. Yes. Okay, so we call this equation 5. So we can also have, or can invert it, sine a over a is equal to sine b over b equal to sine c equal to c, and this becomes equation 6. So any of them is true. You can use any of them to calculate for an unknown angle or for an unknown side. So when is the sine rule used? When do we use the sine rule? So the sine rule may be used when 1, 2 angles and a side are given, 2 sides and 1 angle opposite to one of these sides are given. So let's use a diagram to explain this. Let's take a situation. Let's say this is a triangle. Let's explain 1. Let's say this triangle A, B, C. So when do we use the sine rule? So we use the sine rule when condition 1 is fulfilled, 2 angles and a side are given. So assuming we're given angle A, it will be 47 degrees, and we're given angle B to be 68 degrees. and one side, two angles and a side are given. So either we're given the side that is opposite angle A or the side that's opposite angle D. So let's assume that the side opposite angle B was given to be 7 centimeters. Now, in this case, you can see that two angles and a side opposite to one of the given angles is given. So in this case, we can use sine rule to find the other two sides and also get to know the third angle. So that's the first condition. So if this side is not given, that means this side must be given to me. Let's assume that yes, 3.5 centimeters. Same rule, two angles and one side that's opposite to one of the given angles. Okay, and so that's okay. I'm gonna do this one here like this, and then the next one, when is sine rule used? Sine rule is used when two sides and one angle opposite to one of these sides are given. So it's the reverse. Either two angles and one side opposite the given angle, or two sides and an angle that's opposite to one of the sides is given. We have here, let's say this is triangle ABC also. ABC. So let's assume that here is 3.5 cm and here is 7 cm. So what do we have? We have two sides given, and then an angle must be given that is opposite one of the given sides. So let's say this is the side. So opposite side, either this angle is given, which in this case we might assume to be 47 degrees, or an angle opposite this side, which in this case we can assume to be 68 degrees. You can use any figure, say degrees. So either two sides and one angle that's opposite one of the sides, or two angles and a side opposite to one of the angle. These are the conditions that must be fulfilled if you should use sine rule. If these two conditions are not fulfilled, then they fall into the category of using the cosine rule, which would be the topic that's going to be treated under this topic. So let's move on to calculations.